Okay. So maybe just one or two words on etiquette. I don't think any of us needs really reminding about this at the moment, but microphones and videos are off during the seminar. If you do have a question, you can raise your hand or post it in the chat, and I'll direct it to the speaker, and there's an opportunity to ask questions at the end as well. Okay, so it's my great pleasure, firstly, chairing the session, but equally great pleasure to introduce the speaker, Adeline Fermanian, who is a PhD student at Sorbonne University. The title of her talk is Learning with Signatures. So Adeline, the floor is yours, as they say.
Okay, thank you very much. I'm really glad to be here, and thank you to the organizers for the invitation. So I'm not really working in algebra. I'm doing my PhD in statistics and machine learning. So I will try to give a talk more of an overview of what algebraic objects I use, and yeah, and a little bit of introduction of how it's used in machine learning. So I'm working on signatures more specifically. Yeah, so we begin. So don't hesitate to ask questions during the talk. I will be happy to stop and just discuss. So this is a joint work made by two PhD supervisors, Gérard Biot and Benoît Cadre, who are both statisticians. And so I will begin with a little bit of overview of what's our goal and what's the context. So our context is that we want to learn from a data stream. So what's a data stream? It's any quantity which is observed during time. So it's an ordered object. So I observe value at different times, so there's an ordering. And what do we learn? We can learn different things. First example is time series forecasting, for example. So we can observe financial time series, and we want to say tomorrow how I will be the stock value or something like this. But we can do other things. So for example, in stereo sound recognition, we can want to recognize what people are saying, but with the recording of a sound. So then you have usually stereo sound with two channels. So you observe the two channels and want to say what the person said. But this series can be more complicated. For example, in medicine, you can record a number of physiological variables, and there can be quite many. Here, I think we have 6 or 7. And from these variables, you want to predict something on the state of the patient. It can be another quantitative variable. It can be like diseased or not, or something like this. And a last example is characters or handwriting recognition. So in these pictures, time is kind of hidden. So imagine you're writing on a tablet, then you record the trajectory of your pen. So if you print it, you don't see the time, but actually the time is hidden behind it. And here the task can be easily just to recognize what someone wrote or who wrote it. This is a standard application. So the common feature of all these different applications is that we want to learn something from data which has the form of a path. And what is a path? It is a function x from a time interval, AB, into our d. And d can be actually quite large. So this will be, for most of the talk, our basic object of interest. So, and I will call this a path from now on. So an example I will use throughout the whole presentation is a data set from Google, which is called QuickDraw. So you can see some nice or less nice pictures. So this is a huge data set of 340 different objects that people draw. So we have like a parrot, a hand, and we have many samples. So this is like a character. This is a trajectory, and the task is to recognize what has been drawn. So the question then is, how do I represent such data? So here in practice, what do I have? I have an array of values, and I know the order of the values. So here I have an array in 2 dimensions. This is the x and y coordinates, and I want to represent it. So the first thing is just I draw it as a path. I just interpolate linearly everything. And so we could represent it with the positions. We have this information. So here in blue, it's the evolution of the x coordinate, and in orange, the y coordinates. And actually, this is not a really good representation of, it depends on the application, but often it's not a good representation. Why? Because in this case, for example, if I draw a flower in a reverse order, I get this representation. So this is the same object, but I drew it differently and I have a totally different representation. And another example, if I draw it at a different speed, for example, I go really fast for the first segment and then slowly for the petals or something like this, I get, again, a different representation. So what's the signature? The signature is a way of representing path so that we overcome some of these problems. So it is a transformation, so from this path to a sequence of coefficients of fixed length. So because another common problem with this type of data is that you observe different samples and they have different lengths. For example, different drawings I show, they don't have the same number of points. So with a signature, you map everything to the same a vector of a fixed size. It is independent of parameterization. So this is what I just talked about. So it encodes really geometric properties of the path. And we don't lose too much information in a certain sense of information. So I will now go over some basic properties. So the definition and basic properties, then I will give an overview of how we use it in machine learning and statistics, and then a work I have been doing on really estimation, so from some statistical theoretical guarantees with signatures. So first, the definition and basic properties and a brief history. So everything began with, I hope I'm not saying anything wrong. I think I have experts here. But I think it began with Chen in the 50s. He was the first one to observe that this object of signatures characterizes smooth paths. And then to Reliance extended this to rough path theory. And I would say in the last 10 years, a lot, and especially in the last 2 years, a lot of applications have been rising who use these signature objects in a range of different areas in machine learning. So, so as I said before, everything begins with a path, which I denote xt, and I will assume that it is of bounded variation, so it has a fixed length. And so what's a path? For example, a simple path is cosinus t sinus t on 0, 1. This is, I can represent it like this. In the x-axis is the first coordinate and the y-axis the second one. So this is like the path. So any function can be a path. And what I want to do is to integrate along this path. So imagine for now that it is differentiable and I have another continuous path. I can define the integral of a second continuous function against this path. So what it is, in the case of everything differentiable, this is just a standard Riemann integral of yt against the derivative of a path. So if yt is just 1, I get the increments of a path. So I integrate actually x dot t dt. So I get the last point minus the first point. If xt is just t, then I just get the Riemann classic integral of yt. And another example is if I have 2 coordinates, I can choose to integrate the first coordinate along the second one. And so then if the 2 coordinates are, for example, t squared and t to the cube, I can compute it in closed form. So, and so actually we don't need the path to be differentiable, but just of bounded variation with Riemann Stiglitz integral. And with this definition of integral, I can now define the iterated integral. So now I take a d-dimensional path. So the coordinates are x to the power 1 to d. And I now define what I call the coefficients of signature of first order, which are just the integral of one coordinate. So I have d such coefficients. So I goes from 1 to d. And if I compute it on 0t, I just get the point at t minus the first point. And you can see that the signature is actually itself a path because t can here vary. So we have again a path. And we can iterate this and integrate over any pair of indices. So I get d to the square coefficients Sij. And so I integrate on a simplex. So S has to be smaller than t. So this is not symmetric. Sij is not the same as Sji. And I can again iterate. So, yeah, sorry. So this is again a path because I integrate here on 0t. And if I iterate recursively, I get for any set of indices of length k, this is the signature coefficient along I1 up to ik. And so what I call the signature will be like an infinite vector with all these coefficients stacked. So maybe a better, so yeah, so for example, what number I get. So if I am in 3 dimensions, I get all these possible pairs and triplets of coordinates. So sorry. And maybe as your algebraist, the tensor notation is better. So you can just, group all coefficients of order k in a tensor of order k, which are not xk. And then the signature is this infinite vector with tensors of increasing order, and it lives in the tensor algebra. So I have d coefficients of order 1, d to the squared of order 2, etc., d to the k. So each of these tensors are in space or d to the power k. Is it clear, or are there any questions before I go on with the definition? No. Okay. So an example, if I am in 2 dimensions, so coefficient of order 1 is just a vector, of order 2 it's a matrix, and of order 3 you would get a tensor of order 3. This is like x3. And so in practice, we don't like infinite objects, so we truncate these tensors up to order m. So we call Sm of x the finite vector, and the dimension is d to the power of the order d to the power m. So this is really important because it means that the number of signature coefficients is exponential in the in m, the truncation order. So to give you an idea of typical values, so if I am in 6 dimensions, like in the medical example, for example, I get and m is only equal to 7, I already get hundreds of thousands of coefficients. So in practice, this is a huge limitation, this size. And so I said there is a geometric interpretation. So we integrate. So the signature has information about areas spanned by the path. So here in black, you have a path, and in orange and blue, it's the 2 coefficients of order 2, S12 and S21, which are the areas under and above the path. So this is really geometric. And an important example is the signature of a linear path. So if I take x linear, what does it mean? It's x0 plus the increments times t. Then I have a closed form formula. So this is the signature tensor of order k, and this is just the increments of a path to the power k of a factor of k. So this is really easy to compute. And in practice, we will only deal with piecewise linear paths. So what we need is to be able to concatenate. If we know how to compute the signature of a linear piece, and we know how to compute the signature of a concatenation from each of these signatures, then we win, and we can compute any signature of a piecewise linear path. And this is what is called Chen's identity. So if I have 2 paths, x and y, and I denote by x as star y the concatenation, then the signature of a concatenation is just the tensor products of the 2 signatures. So this is really powerful in practice, because this means we can have really fast packages that compute signatures of piecewise linear paths. And there already exist, several ones exist. So this is, I would say this is the beginning of a story for machine learning, now that we have a way to compute signatures. And so the second, now I will list a number of different properties and explain why they are useful for statistics. So what I said before, it is invariant under reparametrization. So this is quite easy to see because it's defined as an integral. So you can reparametrize the integral to still get the same. So the signature of a reparametrization x tilde is the same as the signature of x. And this is one of the key advantages of signatures. And another interesting property is what happens to the time reversal. So if you have a path X and the X with an arrow is the same, but in the run in the reversed order. And so the signature of X times the signature of a reversed X is actually equal to 1, and 1 is actually the 0 here. So what does this mean? It means that if you consider, so the first coefficient of a signature is always 1. So actually the signature lives in T1 of RD, which is the subspace of a tensor algebra, which begins with a 1. And this is actually a Lie group. And with this 1 as a neutral element. So what I just said is that the inverse of the signature of X is actually the signature of X run in the reversed order. So this is really interesting. And another thing is that we can already see that signature is not unique because, so with chance formula, so this product of signatures is actually the signature of a concatenation of X with itself in the reverse order. And this means that this signature is actually 0. So X run backwards. So X concatenated with X run backwards is the same signature as a null path, a constant path. So signature doesn't see when you go back and forth, basically. And we have also seen that when you reparameterize, signature does not see it. And this is actually the only two things that you don't get when you compute the signature. So this is what we will see now. So to understand how the signature is unique, we define, I didn't do it, it's the paper of Ambly and Lyons of 2010, defined the notion of tree-like path. And this is basically defining an equivalence relation on paths that correspond exactly to the paths that have the same signatures. So they say that two paths X and Y are equivalent if the concatenation of X with Y backwards is tree-like. So I won't give the exact definition, but tree-like is basically an analytic condition. And then this is the same as saying that the signature is 0 if X is tree-like. And then you get this condition. So what's a tree-like path? So we have already seen one. For example, X concatenating with X backwards is tree-like. But we also have, we can again concatenate another path with itself backwards like this. But we can also do something more complicated. So if you consider this last path, so you can see that with chance formula, the signature of this, you can say that it's just the tensor product of all the signatures, and actually Z backwards just cancels with Z, and then you get Y which cancels with Y and X which cancels with X backwards. So this is why the name tree-like, where the name tree-like comes from. You can see you have a kind of tree structure here, like Z is the root, and then you have a Y and Y backwards, and then X and X backwards. So these are the kind of paths that you kind of lose with a signature. All these paths have a 0 signature. So this gives us a uniqueness property. So for any path, you can actually find a unique path of minimal length in its equivalence class for the equivalence relation I just showed. And this is what we call the reduced path. So given the signature of X, you can recover not X, but the reduced path in its equivalence class. And an important property is that if X has one monotone coordinate, then its signatures defines it uniquely. So X is alone in its equivalence class, and you can recover your path. And so this is what we will use in practice, is that if you have some data, to be sure that the signature is unique, you can just add a monotone coordinate. So you lose one dimension, so you get something more dimensional because you have a D, which is now D plus 1, but at least you have uniqueness. And this is what is called embedding or sometimes augmentation. There are different names for this process. So now we have seen in what extent the signature characterizes the path. So basically you don't see when you reparameterize it, you don't see the tree-like pieces, which are pieces where the path goes back and does exactly the same as it did. And we don't see actually translations. I think So this is uniquely up to translations. I forgot to, this is a slight mistake in the slide. So this is basically what you lose. So yes, we can reconstruct the path from the signature, and there are now efficient algorithms. So for piecewise linear paths, this is also a really active area of research when you want less assumptions on the path. So for example, I can show here, so this is like one sample from the quick draw data. This is supposed to be a flower, it's not really beautiful. And so what I did is that I computed the signature and then I inverted the signature, and this is the path I get. So you can see that it kind of smoothed the flower, but I still get the same shape. And so to get endpoints in this recognition, this reconstruction, I need the signature up to order n. So yeah, m. This is what I call m. So we can see and play with data to see what we lose when we compute the signature. So now I would like to talk a little bit about the shuffle product property. So I guess you all know what's a shuffle product. So you consider a permutation of indices from 1 to k plus m. And so sigma is a km shuffle. If you keep the order on the first k indices and the last m indices. So the idea is that it's exactly the same as if you shuffle 2 decks of cards, and you will keep the same order in the cards in your left hand and the order in your right hand. So for example, a shuffle of 1, 2. So I have 1, 2, 3, and I move the 1 between the 2 and the 3. So what's important is that I kept the order on 2 and 3. So sigma here is a 1, 2 shuffle, but sigma here is not a 1, 2 shuffle because I have switched 3 and 2 and I have lost the order here. And so with this definition, I can define the shuffle product of 2 sets of indices. So this is the same as in the definition of the signature. So I have I1 up to Ik and J1 up to Jm. And the shuffle product of I and J is the set of all the indices of length k plus m, such that they have been permuted with a shuffle. So for example, if I have, for example, 1 and 2D, so all the shuffles of 1 and 2D are these ones. So why is it important? Is that you have a nice identity, is that if you take the product of the signature coefficients corresponding to the index I with the one corresponding to the index J, it just equals to the sum of all the shuffles of I and J of the signature coefficients. So basically, when I multiply signature coefficients, this is again linear in the signature. So you have a similar identity for linear forms of the signature. And this tells us that if you take a product of 2 linear forms of the signature, it's again a linear form on the signature. And so the space of linear forms is an algebra. And this gives us the following property with Stone-Weierstrass theorem, that as it's an algebra, you can approximate any continuous function by a linear function of the signature. And this is really a crucial property for statistics, because it means like this f of x is actually like the prediction function. And it means that by just considering the signature, I can approximate it at epsilon with epsilon arbitrary. So it means that the signature and the linear model are happy together. Yeah.
Sorry, Adeline, I've noticed that there's a question in the chat, which I think refers to an earlier part of the talk. Does it always eat the self-intersection? I think it refers to your slide on signature inversion.
The flower, yes, the reconstruction.
Sorry, what's the question?
So the self-intersection disappeared when you reconstructed the image. Is it generally so?
I don't think it's general. So you mean this part?
Yes.
Yeah. I wouldn't say general, no. Mm-hmm. No, you can still keep it. Because here you intersect, right? But
oh, right. Yes, of course.
Yeah. Are there any more questions? No. Okay. So another nice property that the size of these coefficients decrease exponentially fast. So the size of coefficients of order k is bounded by the length of the path to the k of the factorial k. So this is important for approximation properties because, as I said, you always truncate the signature. So it means that the parts you remove from m+1 to infinity, we have a small norm. So it's not a big issue for approximation to remove them. And lastly, I would like to say a few words about something called the log signature. So for this, I will give a few definitions. So I consider the truncated tensor space. So it's the same as before, but I stop at M. So this is a real non-commutative algebra. I have the same neutral element as before, but I just stopped at M. And I define as before the space T1M, which has a 1 as a first element, and T0M, which is a 0 as a first element. And so with this space, on these spaces, I can define the exponential and the logarithm with a power series. So for any element in the tensor space Tm, I can define its exponential as the sum of a to the tensor power k. And if the first element is 1, I can define the logarithm in the same way. And as the signature is the first element equal to 1, you can see that the log signature is an object well defined that you can compute. And so also it's worth saying that the exponential and the log are isomorphisms and each other inverses. So from the log signature, you get the signature, and from the signature, you can get the log signature by taking the log and exponential. And so the log signature is actually a really interesting object because it will help us understand the space where the signature lives. And by understanding where the log signature lives, and the log signature actually lives in a Lie algebra. So for this, I define the Lie brackets as here, and I can define the Lie brackets of linear subspaces of Tm. So this is just the span of the elements in F1 and F2, of the Lie brackets of the elements of F1 and F2. And with this, I will define recursively the following space. So L0 is just 0, L1 it's all RD, and then I take the bracket products of RD with itself and I iterate. And I consider the space of Lie former series, which is a subspace of Tm of RD of all the elements, which can be written as this form. So each of the Lk is in this Lie brackets space. And actually what we can say is that any element of the tensor algebra, it is the signature of a smooth path if and only if the log of A is in this space. So we exactly know in what subspace of the tensor algebra the signature lives. And this also tells us the dimension of the log signature of a vector space where the log signature lives, and it is much lower dimensional than Tm of Rd. So the log signature is a really lower dimensional representation of the signature, but the drawback of using the log signature is that we lose the linear approximation property that I gave before. So basically we can use it to lower the dimension of the spaces, but then we don't have strong approximation properties as before. So to give you an idea of the different dimensions, so this, in orange you have a size of a signature, and in green the size of a log signature. And so you have basically a power of 10 of difference. And this can be really huge, really fast. So yeah, that's it for the properties. So I've tried to kind of give the algebraic properties of a signature. And now I will focus on how we use this in machine learning, basically. So a few words on supervised learning. So I will place myself in supervised learning. So now what's our goal is to understand the relationship between two objects which live in X and Y, which live in two different spaces. And Y is so X is the input and Y the output. So in regression, for example, Y is just a real number. In classification, it is more a label. And I observe some data, X1, Y1 up to X and Yn, which is IID with the same distribution as XY. Basically. And what I will do, I will try to build a function f theta so that f theta of X is close to Y. And theta is a vector which I will have to find. So I have to specify what's the function f theta, and I have to find what theta is. So for example, in the quick draw data, X is a path. So this is like the trajectory of a pen, and Y is a label saying what object it is. So for example, flowers are labeled as 1, cars as 2, a plane as 3, etc. And now how do I do this? So I define a loss function, L from Y times Y into R plus, which quantifies how different are two elements of Y. And I will just choose a parameter theta hat that minimizes the sum of the loss on the data. So I take the loss of the data Yi and f theta of xi, which is my prediction, which is supposed to be close to Yi. And I sum this over all the data points I have. So for example, in least squares regression, I just take the L2 norm on the two between Y and f theta of X. In binary classification, I can take the 0, 1 loss, which is equal to 1 when I predict the right label and 0 otherwise. Basically,
we have another question, Adeline.
Yeah.
Does the person who asked it want to present it?
Adeline, my question is the following one. It's a very short one. I have a sequence of tensors of order k from 1 to infinity. Is it does it exist a path connected to that sequence? When a sequence of tensors is a signature?
So if the log of this sequence is in the space that I wrote just here.
Okay. And
in this case, yeah, there exists a path such that you have a signature of it.
And,
yeah.
and the immediate question is: have you a way to check that the log of the tensor it belongs to the domain in which you are looking for?
I don't think anyone has done that. I don't know, but I don't know anything about that. Yeah, this is a good question. Yes. Yeah.
Thank you.
You're welcome. Okay, so this was really quickly the principle of empirical risk minimization in supervised learning. So an example of, so what is f theta? So for example, if you have a neural network, this is f theta is just equal to this kind of function. So you have the composition of L functions. So L is what we call the number of layers. And each TL is just an affine function. And rho is a nonlinear function. So this is, for example, the max between its argument and 0. And sigma is just the output. It maps. So here you get a vector, and sigma maps it to the kind of output you want. So either another real number or a label. And so in this case, what is theta? Theta is just the concatenation of all the parameters in TL. So WL and B, so WL is a matrix, BL is a vector. So theta would be a really huge vector with all these parameters stacked together. So typically, and then you would have to find this TL, WL, and BL with a specified loss that you minimize, for example. So where do signatures come into the story? So if you have your path X, for example, a simple thing you want to do is just from your path X, you compute its signatures, and then you say that this signature is the input of your f theta function, which can be a network, but anything else also works, and then you can predict something. So this is the approach of some people, so for example, of Yang et al., who worked on human action recognition with signatures, and the idea that they were able to use a really small network by working on this vector of signature. So they worked a lot on having good signature coefficients, and then they were able to have a really simple network, whereas usually people use huge networks and don't do much work on the input data. So this is basically one idea, but there are many other methods that use signatures. So I said before that the signature, if you don't compute the signature of the whole path, you get again a path because you can compute the signature of sub-pieces. And so this is what I call temporal approaches. So you can construct a path of signature coefficients. So you just divide your interval, and then you can take each of these pieces, take the signature, and this is again like a sequence of vectors, and then you can use an algorithm adapted. So an algorithm that is able to take as input an ordered sequence. So this has also been used a lot with signatures. And the last idea is only works when you have paths in R2, so which is the case of a quick draw data, but it's not the case, for example, with the medical time series that I showed, because D was much larger. And in this case, some people have played with signatures and created pictures of signature coefficients. So basically you play by sometimes considering your path as an image and sometimes considering it as a function. And in this case, you can basically, for each index I, I1 and 2ik, you can construct one image. And this is what I represent here. So you see you have one image of order 0, 2 images of order 1, 4 images of order 2, 8 images of order 3, etc. And then you can use this with deep learning algorithms adapted to images, because these work really well and are well known. So usually what you have when you do recognition with images, you have 3 input images, which is like red, green, and blue. And here, instead of having the colors, you have a signature, a set of signature images. So this is also another approach which has been used quite successfully for Chinese character recognition, for example. So yeah, I won't go into this. So basically, the idea was to give you an overview of what type of things you can do when you have defined a signature and which properties are useful. And so to sum up, the global idea that you have your data, you map it into a continuous path, you compute the signature one way or another, and you plug it into an algorithm. And in the time that I still have, I will talk a little bit on how could we choose the M, because throughout until now, I have always assumed that M is chosen and is fixed. And I will show one study we have done on how should I choose M. So this is what I call the truncation order selection. And or maybe if there are some questions now on what I've said until now. No, okay. Then I will go on. So now I have some probability too. So I consider that I have an input path X, which is random, and an output variable Y. So I am in a regression context. So Y is a quantitative variable. And I will assume a linear model. So what do I say? I assume that the expectation of the output Y, given my input X, is a linear function on the signature. So this is the signature truncated at a certain order M star with a scalar product on the beta star. And both beta star and M star are unknown quantities. So I have to find a way to estimate these from the data. And I will also assume that the variance of Y is uniformly bounded by sigma square. And with only these assumptions, I will describe a procedure to estimate the value of M star and beta star. So how do I estimate it? I need some data. So I assume that N data points. And I will assume that all the coefficients I will consider lie in balls. So I will bound the norm of beta by alpha for any size of beta. Yeah, something I forgot to say that, so the size of beta star depends on M star, right? Because this is this has size basically d to the power m star. So when m star increases, beta star increases. So the two are linked, they're not two independent quantities. So for any size m, I assume that beta is bounded by alpha. And then I am able to consider, so this is the 1/n sum of the losses, like before, like I defined empirical risk minimization, and now I take the L2 loss, and I take the difference between yi, the data point I, and its linear form, a linear form of the signature, truncated at m. So for each size m, I have a loss, Rmn of beta. And I will minimize it on the balls, Bm alpha. So this gives me a quantity which only depends on m and not on beta, which is basically the minimum loss for any beta in the balls of radius alpha. So you can see that when m increases, you have more and more flexibility on beta. So at a point, you can basically, this can be 0. If m is large enough so that d to the m is equal to n, this is 0. So L hat n of m is a strictly decreasing quantity. So to find the best size m hat, I will penalize it. So I will take the minimum of this strictly decreasing quantity plus a penalty that I have to choose carefully. And so here you can see, so in blue it's the loss, which, so the x-axis is m, the y-axis is the value of the loss. So in blue you have a loss, which is strictly decreasing, and in orange, this is a specific penalty, and in green, this is a sum, and here I would choose the value minimizing this sum, so I would choose m, the truncation order equal to 5. And so now what we have to do is to find the right function that we have to put here so that m hat converges to the true m star that we don't know. So for this, I need two assumptions. So I assume that the true coefficient is also in a ball of radius alpha. And I also assume that both y and x are amorphally uniformly bounded by ky and kx. So everything is basically bounded. And then I am able to show that for a specific penalty, which is, so basically this is the square root of the size of a signature divided by n to the rho, and n and rho is just smaller than a square root. So this is just a little bit smaller than the square root of d to the n over n. And so under all the assumptions with this penalty, we are able to show that the probability that we take the wrong truncation order decreases exponentially with n. So yeah, that's the kind of, that's it. So this tells us that m hat converges amorphally towards m star when we have more and more data. N is the number of data points. And with this, we are also able to estimate beta star by just taking, so the minimum, the argmin of the loss for this size m hat. So with this, we have both m hat and beta hat, and we have like a bound on the L2 error of the regression function. So this is a function that we will use to predict. This is the true n function, and this is basically a big O of 1 over square root of n. So this means that when we have more and more data, we will make less and less mistakes. So yeah, and so we can apply this procedure. So this is also a procedure that can be directly applied, right? This function. So not directly because I don't know this constant here, but there are some classic ways to tune it. And so when we have tuned the function k, we are able to apply it. So here, this is a quite easy data set, but so these are like, this is the temperature in different locations in Canada. And I want, from the profile of the temperature of the year, I want to predict the total annual precipitations. So y is just a real number, and I observe the whole curve of temperatures over different locations. And so to do this, I can just apply a linear model, as I said, and this, I compute the signature of each temperature profile. I compute beta hat and m hat, as I said before, and I can predict the precipitation. So here I found the best m hat was 5. This is the curve I showed at the beginning. And here I plot, so in the x-axis, it's the true values of the precipitations, and in the y-axis, it's what I predict. And you can see that this is close to the bisector. So this means we basically, we don't do much errors. And so this is, whereas this is a really simple model, it's just linear on the signature. So the signature has enough expressive power to approximate these kind of functions. So yeah, so this is an example to show that it can work pretty well. An interesting thing to look at, it's the coefficient beta hat that you can see is quite sparse. So you have a lot of coefficients which are equal to 0. So this is something we would like to investigate in the future, how this sparsity is organized. And I will quickly also talk about how you can, so this can be adapted to classification. So when y is in, for example, so binary classification, y is in 0, 1. So this is not the best way to do it, but an easy thing to do is just to predict 1 if y hat is above 0.5 and 0 otherwise. So I can just use the same model and just say 0, 1 are real values. And we did this. So this is not what people do usually with classification, but this was just a straightforward way for us to adapt this model to classification without having to do anything theoretically. And so we applied it on really classic data sets to see how it works. So, and we wanted to see the typical values of M hat that you find in practice. So we used 26 data sets which have very different characteristics. And so you can find that basically M hat is between 0 and 10. So it's not never above 10 because the dimension explodes. And here is like the expected, so this is the basically, so in the x-axis, it's a benchmark, and the y-axis is our performance. So you can see that we are not too far from the benchmark, whereas we used a really basic model. So usually it's really not a good statistical model, but it's a simple one, and we already do quite good. So this was a really promising results. So to conclude, we were able to have theoretical guarantees on a linear model with signatures, a model that can be implemented in practice, and which is generic. It has really few assumptions on the data because we can have any dimension on the data and we can have interactions between the different dimensions. We don't do any assumption that the function has a specific form, the f, so it has to be a kind of continuous, but nothing more. Which is, and usually people so there's a field called functional data analysis, and which basically deals with this kind of data. And usually they have to do really strong assumptions on the functional form of f theta. And it has good performance. So it's really promising. And even with a simple model, we have a really good performance. And there are a lot of open questions. So for example, sparsity that I talked about. I would be really interested in giving some theoretical results with log signatures, because log signatures are, but they are a more complicated object to deal with, etc. So yeah, that's it. And thank you very much for your attention. I hope it was interesting to you.
Thank you very much, Adeline, for a very, very nice talk.